Okay, so should we get started? Ronan, are you ready? Hope you're muted.
I'm ready.
Great, cool. Okay, so it's right at 8 a.m., but we're on a pretty tight schedule, so let's get going. So welcome everybody to the very first session of Random. Raghu, do you want to say something to introduce the conference in general, or shall we just jump into talks?
I mean, nothing in particular except to say welcome everybody. This is new for most of us again. Hopefully we'll make the most or maybe even better than the actual physical conference. So let's just go ahead.
Indeed. Okay, thanks. Yeah, so with that, our very first talk is by Ronan Schofield, who will be talking about, is it possible to improve Yau's XOR lemma using reductions that exploit the efficiency of their oracle? So take it away.
Okay, so can you hear me?
Yes.
Very good. So good morning or afternoon or evening, everyone. So I'll be talking about Yau's XOR lemma. So Yau's XOR lemma is a hardness amplification result. Namely, it's a way to transform mildly hard functions into very hard functions. More specifically, if you give me a function f such that for every circuit in some circuit class, think p/poly, the probability that the circuit computes the function f correctly on a random input is smaller than, say, 1 minus 1/3, and I'll call such a function a 1 minus 1/3 hard function. What Yau's XOR lemma says is that if you consider the function f XOR t, which receives t inputs, x1 up to xt, evaluates f on each one of the inputs and XORs the output. So if you consider this function for sufficiently large t, then for every circuit C prime in the circuit class, the probability that the circuit C prime computes f XOR t correctly on a random input is less than half plus epsilon. So we started from a 1 minus 1/3 hard function, and we got a half plus epsilon hard function, and the precise statement of a lemma, for example, for p/poly, is that for every function f, if we take sufficiently many repetitions, if t is slightly more than log n, then for every constant c, we can get a half plus epsilon hard function for epsilon, which is 1 over n to the c. And that's great. We all like this lemma. There are many proofs of this lemma, and it's very useful in crypto and randomization because we like half plus epsilon hard functions. But there are still open problems about Yau's XOR lemma. There are still things that we don't know. And here are two specific problems. The first open problem, if we consider the class p/poly, as I said, we can get a half plus epsilon hard function for epsilon, which is 1 over n to the c for every constant c. But can you get epsilon to be below that? Can you get epsilon, which is 1 over n to the omega of 1 subpolynomial? We don't know. The second open problem is concerning the class AC0 with parity gates, namely the class of constant depth circuits that are allowed to use gates and or not and parity. And here, we don't even know if you can get epsilon, which is 1 over n. We don't know how to prove an XOR lemma for this class. And both these open problems are open, even if you take t not to be logarithmic, like log n to the 1.1, but even if you take t to be something like polynomial in n. We just don't know how to solve these two problems. So what do complexity theorists do when we can't prove something? We make excuses. So there's a long line of work of making excuses, and there's a hierarchy of excuses, starting from very weak excuses, like the dog ate the proof, to very good excuses, like you can't prove what you want to prove with all existing proof techniques. So obviously, this is the kind of excuse that we want. And in the middle, we have something like you can't prove what you want to prove with black box techniques. And the long line of work I was telling you about achieves this goal, and achieves this goal. And today, in a joint work with, 2 years ago, in a joint work with Greenberg and Viola, we proved that even if you take the most general black box techniques that we can imagine, adaptive, non-uniform black box techniques, then you still can't prove, you still can't use these techniques to prove to solve the two open problems about Yau's XOR lemma. So today we are here. The problem is that this is not a very good excuse because there are related results in the literature that use non-black box techniques. So this is the first result that I'm aware of in a related context of hardness amplification is with Gutfreund and Tashma. But the most famous result that we have now is by Hirahara from 2 years ago. Hirahara gave a worst case to average case reduction for for languages in NP, which uses non-black box techniques, and specifically it uses a technique which I'll call class reductions, where the proof relies on the efficiency of the adversary C prime, which is trying to break F XOR T. So at the moment, in a related context, we have other techniques which are not covered by the excuses, these class reductions, which are non-black box. Moreover, in these related areas, class reductions, these non-black box techniques, provably break limitations on black box techniques. So the excuse that we have is not so good. So what do we do in this work? I would have loved to tell you that we improve Yau's XOR lemma, but instead what we do is we improve the excuse. So in this work, we improve the excuse, and we say we can prove impossibility results even for class reductions and even for a strong flavor of class reductions called non-uniform class reduction. And the main contribution here in my mind is that we can prove impossibility results even for some non-black box techniques. This demonstrates that we are able to prove impossibility results even for some non-black box techniques. And I should probably say that there's a discussion in the paper about whether we cover the most general definition of class reduction. So if you're interested, go to the paper. I don't have time to talk about it. What I do want to talk about is I want to tell you what is the definition of this class reduction. So let's start with what is a black box reduction. What is a black box reduction? We need to show that if F is 1 minus 1/3 hard, then F XOR T is half plus epsilon hard. And we're interested in proof by black box reduction. So what is a proof by black box reduction? This is an oracle procedure, a reduction, such that if you give the reduction access to any function C prime which breaks the security of F XOR T, then when the reduction receives oracle access to this function C prime, to this adversary, it breaks the initial function F, okay? So for every C prime, if C prime breaks F XOR T and you give me C prime as an oracle, as a reduction, I will be able to break F. What do we mean when we say black box? So when we say black box reductions, we typically mean two things. The first thing that we mean is that the reduction interacts with its oracle using queries. Specifically, here I wrote down the oracle. I wrote the truth table of the oracle. It's an exponentially long truth table. And since we imagine the table is in this black box, the reduction is only able to communicate with it by asking queries and receiving answers. But a second requirement that we make from black box reduction is that for every function C prime, even an inefficient one that breaks the target function F XOR T, the reduction needs to break F when given oracle to C prime, even if C prime is inefficient, right? Which is not necessarily something that we need in order to prove a lemma. So when we move from black box reduction to class reductions, what we do is we modify this second item. So we no longer consider every C prime. We only consider a function C prime, which come from some efficient class of functions, say P/poly or AC0 with parity gates. So a class reduction is a reduction, but only needs to perform if it is given oracle that is efficient. This is the new component in this work, for example, in this famous work by Hirahara. And the main result of this paper is that it is impossible to solve open problems 1 and 2, even if you use class reductions. And in fact, even if you use a very strong flavor of class reductions, but are allowed to receive non-uniform advice on the oracle C prime. So you can take a look at the longer version of the talk or at the paper if you want to know more about this. So let me right? I mean, put on the conclusion slide. If I have more time, I can go over it, but if not, I'm done, and I'm ready for questions.
Thanks. I'll clap. Yeah, so there's a question in the chat box. Ronan, can you see the chat box, or shall I read it out?
I'll try to look at the chat box. Do I?
Maybe in the interest of time, I'll read it while you're figuring it out. So Shuichi Hirihara asks, can you extend your results to the case of errorless average case settings?
So I haven't thought about it, right? And so I'm answering without seriously thinking about it, but related impossibility results can be extended to errorless reductions. So I'm guessing that maybe the answer is yes, but I'll have to think about it and check.
Thanks. Okay, so we're at time, so unfortunately, I guess that's it for questions, but thanks for the nice talk. And next up, who's giving? Is it? I saw Sumega was here. Or is she giving
giving the talk.
Great. Can you share your slides?
Yeah.
So next, we have Sumega Garg talking about joint work with Pravesh Kathari and Ron Raz, time-space trade-offs for distinguishing distributions and security of Goldreich's PRG.
Hi, thanks Mary for the introduction, and thanks the organizers for organizing this workshop, this conference. So today I'll be talking about time-space trade-offs for distinguishing distributions and applications to security of Goldreich's PRG in the streaming model against memory-bounded adversaries. So this is joint work with Pravesh and Ran, and thank you all for tuning in. Okay, let's start with the generator proposed by Goldreich in 2000. What this generator does is it takes an n-bit input and outputs m-bit string where we want m to be greater than n. And it does as follows. It fixes a predicate p, which is a k-ary Boolean predicate that takes in k bits and outputs a single bit. And it also fixes m subsets of 1 to n, which are of size k. And given an n-bit string, we would represent the projection of x to coordinates of Si by x subscript Si. So x subscript Si is a k-sized string. So what G does is it takes this n-bit and outputs an m-bit, where each bit of the output is the output of P on projection of x to one of these subsets. And it concatenates all these outputs together and it generates the output string. So this is a proposal for a candidate local PRG construction, where by local, what one means is that each output depends on only a very few bits of the input string. And informally, a PRG is such that the output of this G is indistinguishable from a random m-bit string for adversaries with limited resources. And these limited resources can be defined under various restricted classes. And there have been many works evidencing the security of Goldreich's local PRG against restricted classes of attacks. And these classes of attacks mostly are motivated from proving security against time-bounded adversaries. And the focus of this talk is to prove security against memory-bounded adversaries. I want to mention this line of work that considers the attacks that can be generated using STPs, and these papers identify t-resiliency of P as a necessary condition for the security when m is n to the order t. Here SIs are random subsets, k-size subsets of 1 to n. Note that the stretch m, that is the output of G, can be at most n to the k, because that is the number of subsets, k-size subsets of 1 to n. So this t-resiliency property is also important, shows up in our proof of security against memory-bounded adversaries in the streaming model, and I want to elaborate on this property a bit more. So P is a predicate that takes in k bits to 1 bit, and it is called, it is called t-resilient if P has zero correlation with every parity function on at most t minus 1 bits. That is, for all alpha which are n-bit strings such that alpha has at most t minus 1 once. If you consider this parity function, that is, it takes in another n-bit string x and outputs summation I alpha I xi mod 2, then for all alphas that has at most t minus 1 once, p has 0 correlation with this parity function. Then this is called a t-resilient predicate. So let me elaborate on our model a bit more. So we prove security of Goldreich's local PRG against memory bounded adversaries in the streaming model, where predicate P is fixed and X is chosen uniformly from 0, 1 to the n. And this is unknown to the adversary. This is thought to be as a seed of the generator G. And a memory bounded adversary either sees output of G in a stream or a random m-bit string. Let me elaborate on this a bit more. That is, at each step I, Si is a randomly k-sized subset of 1 to n, and a distinguisher either sees a stream of Si, the output of P on projection of X on Si, or Si, Bi, where Bi is a uniform 0, 1 bit. So the first stream can be thought of as the generator, as output of the generator G, where X is chosen randomly and then fixed, and the second can be thought of as a uniformly random string. And note that in this model, we get to see the SIs at each step. So what we prove is that if P is a t-resilient predicate, then in this streaming model, Goldreich's local PRG is secure against all adversaries, which has at most n to the epsilon bits of memory, as long as the stretch is less than n to the order t. So I want to move on to our second result for distinguishing distributions here, where we consider the question of distinguishing subspaces from uniform distribution over 0, 1 to the n. So here in the first distribution, there is a pseudorandom subspace source of dimension k, which chooses a random k-dimensional linear subspace and draws samples uniformly from this fixed subspace S. Whereas in the second model, in the second distribution, the uniform source draws sample uniformly from 0, 1 to the n. And we want to distinguish between these two cases. So we prove that any algorithm that distinguishes between uniform and subspace source of dimension k requires either k-square memory or at least exponential number of samples, where exponential is in k. So to conclude, I want to mention a couple of motivations for these results. The first one is that it adds to this field of bounded storage cryptography that considers cryptographic protocols that are secure against memory bounded adversaries. And the second fascinating application is in average case complexity, where we show that refuting random CSPs with t-resilient predicate is hard for memory bounded algorithms. I don't have time to go into the proof techniques, but please refer to the longer talk to learn about them. Thank you.
Thanks. Are there any questions? You can either ask in the chat box or just unmute yourself, or I don't know if you're allowed to unmute yourself. If you are, go ahead and ask, and if not, raise your hand and I'll unmute you.
So I have a question. Do the sets SI have to be completely random for the first result, or can you have them satisfy some weaker properties?
That's a good question. So, okay, I will have to think about it a bit more, but my intuition would be that it should work for high entropy distributions on SIs.
Okay.
We have time for one more quick question if anybody has one. If there are no more questions, yes, let's thank Sumega again. Oh, sorry, there is a question. Clement asks in the chat from Clement Clenon, for the distinguishability of distribution case, is there an information theoretic lower bound of 2 to the n over 2 samples as well?
So do you mean by like under memory constraints? Otherwise, we can just like, if we don't have memory constraints, we can store n samples and figure out if it is n minus 1 dimensional or n dimensional.
Okay, Thanks. Yeah, my question was just, so
Yeah.
the restriction, the fact that it is a linear subspace really makes it easier otherwise. If it was just, yeah, okay. Thank you.
Thanks.
Okay, so thanks Megan again. Next up, we have Shuichi Hirahara. Are you going to give the talk? Sounds good. Okay. Yeah, so next we have Shuichi Hirahara and Osamu Watanabe, excuse me, on the non-adaptive security reductions of hitting set generators, and Shuichi will give the talk.
Thank you for the introduction. Can you hear me? Okay. Well, okay, so the main question we are concerned with this work is the relationship between worst case and average case compressive NP. Specifically, assuming that NP is different from P, can we prove that NP is average case hard in the sense that dist NP is not a subset of average P? Here, dist NP is an average case version of NP, and it consists of a distribution problem where L is an NP question, and we consider efficiently samplable distribution on it. Average P stands for average case polynomial time algorithm, and here we are going to consider errorless average cases heuristic notions. There has been a long line of research on why it is difficult to resolve this open question. For example, we know that there is a relativization barrier for resolving this open question. Another barrier is what we call limits of black box reductions, which is going to be the main focus of this work. In order to explain the notion of black box reduction, let's try to resolve this open question by the following naive approach. In order to resolve this open question, it suffices to design a polynomial time reduction that solves some NP complete problem L that makes a bunch of queries to some heuristic algorithm that can solve some problem in this NP problem. And given the answer, we'd like to solve some NP complete problem. If we can do that, we can resolve the open question about worst case to average case reduction about NP. Most reductions in complexity theory is what we call black box reduction, in the sense that the reduction works no matter how inefficient oracle you are given. But unfortunately, we have limits of such a black box reduction techniques. Bogdanov and Trevisan showed that there is no such randomized polynomial time non-adaptive reduction unless NP is a subset of co-NP/poly, which is quite unlikely. So we should use a different approach. In fact, not only NP, it is still open question to prove the corresponding open question about pH. To be specific, if assuming that pH is different from P, can we prove that pH is hard in the average case sense? Well, this is an easier question than the corresponding open question about NP, because in the case of worst case, we know that the worst case compressed of NP is equivalent to the worst case compressed of pH. So the point is that before trying to prove the open question about NP, we should first try to prove the open question about pH. But regarding this easier open question, we have rather poor understanding of why it is difficult to resolve this open question. There is some limits about this open question, but regarding limits of black box reduction, we didn't know any limits of black box reduction before. And what we showed in this work is the first limit of black box reduction from NP to some form of distribution of pH problem. Specifically, I'm going to restrict ourselves to the case of where some form of distribution pH problem specifically, I'm going to consider only the task of avoiding pH compatible heating set generators, and then I will go to present a limit of such proof techniques. A heating set generator is a fundamental notion in the theory of de-randomization, but instead of de-randomization, I'm going to use the heating set generator in order to construct an average case hard problem. So this is the definition of a heating set generator. But what's important is that if we can construct a heating set generator, which is computable in pH, then we can get an average case hard pH problem. The reason is that we can just consider the distribution problem of testing the membership in the image of H under the uniform distribution. In fact, this is a quite general approach because in a subsequent work, I was able to prove the compass direction as well. So this is a general approach to prove average hardness of pH. So in light of this, we can consider the following approach to prove the open question about distribution pH. In order to resolve this question, we would like to design a black box reduction, which makes a bunch of queries to some average case algorithm that avoids a heating set generator, where H is some heating set generator that is computable in pH. If we can design such a polynomial time reduction, we can resolve this open question. And what we showed in this work is that unfortunately, there are limits of black box reduction. What we showed is that for any function H, we can't hope to get such polynomial time reduction, which is randomized and non-adaptive reduction, unless L is co-NP/poly, or otherwise the seed length should be quite close to the output length. More generally, we have this result, which basically says that if a problem L is reducible to any oracle that avoids a heating set generator by a randomized polynomial time non-adaptive reduction, then we have some upper bound, something like NP/poly and co-NP/poly. Moreover, if H is computable in exponential time, then we get an improved upper bound of AM intersect co-AM. Previously, good following upper down showed that there is an upper bound of BPP to the NP, and our result improved it to AM intersect co-AM. Thank you for your attention.
Thanks. Are there any questions? Again, you can ask in the chat or just unmute yourself and ask. Okay, so if there are no questions, I guess let's thank Shuichi again. Thank you. And we have about 1 minute until the next talk is supposed to start. So I guess if the next speaker can set up. I set up here, I guess I just mean share your screen.
Hi, Anna.
Let's wait just a minute so that if folks are tuning in just for this, they don't miss the first minute. Okay, so I guess we can go ahead and get started. Mika, you ready?
Yeah.
Cool. Okay, so our next talk is joint work by Shalev Ben David, Mika Goose, Robin Kothari, and Thomas Watson. When is amplification necessary for composition in randomized query complexity? And Mika will give the talk.
Okay, thanks. Okay, hello everybody. So this work concerns query complexity or decision tree complexity. I hope people have seen decision trees before. They're maybe one of the oldest and simplest models of computation. They look something like this. They are a way to compute a Boolean function on an unknown input. So you start querying individual bits of the input. That is like tracing a path in the tree from the root towards a leaf until you've queried enough of the bits that you can produce an output bit. And so for any Boolean function, you can ask, what is its query complexity? Meaning, what's the best decision tree computing the function? So here, best means the least height of a decision tree, the one that uses the fewest number of queries. So decision trees, they've been studied for, I don't know, maybe half a century. And one of the very typical situations that you run into when you study them is you want to understand more complicated functions, their query complexities, based on how they're composed or their constituents. So suppose, for example, you have two Boolean functions, f and g, on n bits and m bits. Suppose you understand their query complexity completely. Well, what about if you composed the two functions and constructed this more complicated object? So the composed function looks something like this. You put your f and you replace each of the input variables to it with a copy of g. So you have n copies of g. They are fed disjoint sets of variables. So altogether, the composed function has some m times n many input bits. So suppose you understood f and you understood g. Can you understand the query complexity of the composition? It's a very natural question. And in some cases, the answer is plainly yes, we can understand it very well. In the most basic setting, the deterministic query complexity, deterministic decision trees is what I've been talking about so far. We do have complete understanding. The query complexity of the composed function is simply the product of the individual complexities. And this is not even hard to see. In fact, let me just sketch why is it that if you have both a decision tree for f and one for g, you can efficiently construct one for the composed function. So if I just go back a slide, how would you do that? You would compose the decision trees. So a decision tree for the composed function you can obtain by running a decision tree for f, and whenever the decision tree queries one of its input bits, say the second one here, you just invoke as a subroutine a decision tree for that particular copy of g. So again, every time you query something for f, you run a subroutine for g. And that results in, well, this amount of queries being made. It's also a lower bound, not hard to see. It's also true even in more complicated settings, something called quantum query complexity, that for the composed function, its query complexity is multiplicative. Okay, now up to constant factors, but this was a really deep theorem proved roughly a decade ago. Well, the focus of this talk is the randomized case, which is still not completely understood. So I should say here that a randomized decision tree is one that is allowed to toss coins and is only allowed to output the value of the function with high probability. So maybe 2/3 of the time it gives the right answer, but it may err 1/3 of the time. And so here, we don't even know what the answer should be. It really depends on f and g. And here's one side of the coin is what can we guarantee is a universal upper bound for the complexity for any f and g. We are not going to achieve the mere product of the two individual complexities. The best upper bound has this mysterious log factor appearing. And I can tell you why that is actually. It's, if you remember back to the deterministic case, we invoked this decision tree for G as a subroutine. But now we only have a subroutine that is returning the correct value with probability 2/3. So again, 1/3 of the time, maybe it gives back the wrong answer. And now we have several subroutines for many copies of G. They're all giving me 1/3 error. So if I keep invoking them, it's very likely that some of these subroutines are giving me wrong answers. And that's why the construction gets stuck. The way around this is to introduce a log factor and take these subroutines that had 1/3 probability of error and run them roughly log n times and take the majority answer in order to reduce the error probability for one subroutine below 1/n. So then that's such a small error that it doesn't pile up during the simulation. So that's the intuitive reason why a log factor appears in the upper bound. And now the sole focus of this work is simply to show that in some cases, this upper bound is tight, that there exists a choice for F and G where you do indeed need the log factor. You need to amplify this success probability for the subroutines. So we show this for a particular choice of an outer function, kind of a natural one, XOR of n bits, or we can do it for the majority of n bits, and also a careful choice for the inner function. We actually think that the inner function need not be chosen carefully, and the conjecture is that actually you need amplification for composition already if you just have one of these XOR or majority as your outer function, no matter what the G is. And in fact, this was already proved for XOR a couple of weeks ago in a work of Josh Brody and his students. So already one of the open problems in our work was solved, but it's still open to show such a super composition theorem for majority being the outer function. So yeah, I should leave it at that. Okay, thank you.
Thanks. Are there any questions? Again, just ask in the chat box or unmute yourself and ask.
It's maybe a silly question, but don't you need some constraints on G?
Yeah, so that's why it's in quotation marks. The actual conjecture is a little bit more complicated. You have to rule out some counterexamples. So the actual expression is something like the bounded error complexity of F times the expected number of queries you need to reach error 1/n.
Okay.
I have a question. So is it for partial functions or total functions?
Okay, so our examples are, there's a partial function right here. And it's open for total functions. If you prove it in this more general case, then you also get it for a total function, because we know of total functions who have this behavior that its query complexity increases if you need to reduce the error, which is not even obvious how to do it for total functions.
Thanks.
Any more questions? Okay, if there are no more questions, let's thank Mika again. And let's thank all of the speakers in this session. So, thanks, everybody. And now I guess we have a 20-minute break, and we'll be back at 9 a.m. Pacific time for a talk by Shahar Levitt. So see you in 20 minutes.
Thank you.